In part 2 of section 6, we're going to be looking at graphing a linear function. And we've already addressed the idea of graphing in two ways this semester. We've done the make a table method, and we've also done the transformation approach, where we have a group of parent functions, a library of parent functions to be familiar with, and then we can apply the stretches and shrinks and reflections and shifts, and we can get our graphing done that way without having to have a table. Well, when it comes to a linear function, you don't even need to make a table, nor do you need to do transformations to be able to get this graph completed. And the reason for that is because a linear function is always going to form a straight line. So in order to be able to draw a straight line, there's really only two things that you need. You need a starting point, which is what I'm calling the ordered pair, and you need some direction to go in. If I was asked to draw a line to go through this point, there would be an infinite number of ways that I could draw a line to go through that point. Here's just a few samples of that. So to be more precise, I have to have one specific direction that I'm supposed to go in, and this is what we call the slope of the line. So if I have a specific slope in mind, and we'll talk about this with the next definition, if I go up a certain amount and then over to the right a certain amount, then I can place a point here to represent the direction that I want my line to go in, and then I can also carry it down in the other direction to get the full length of the line. So we don't need a table with a bunch of values. We don't need to worry about transformations for this. If you can recognize that you're dealing with a linear function, all you need is one point and the slope will lead you to a second point, and that's how you can draw your line. So definition 6.2 is going to get us a little more information about the idea of slope. So for those that have never seen slope before, make sure you pay close attention to this, because this is a very special feature of the linear function, because it has a constant slope no matter where you look on the graph. So we use the letter M to represent slope, and we're going to talk specifically about the slope of a non-vertical line. We'll talk about vertical lines more in the future, and it says a non-vertical line that passes through the points A and B. So I want to draw a picture to go along with what we're describing here for the slope. So I'm just going to focus on the first quadrant for this illustration, and there's going to be a point. We're going to call that point A, and there'll be another point. We'll call that point B, and there's supposed to be a line that passes through these 2 points. So I'm just drawing precisely what that first statement says there. And then it says M, which is called the slope, represents the change in y divided by the change in x. So slope is always a ratio. It's a ratio that compares the change in y to the change in x from point A to point B. So when I'm looking at this this picture that I've drawn, the change in y, if I start at A, I would have to go up a certain amount until I got to the same height as point B. And then once I got to that height, then I could start going to the right until I got over to where point B was located. And that's not exactly the best picture of that. Let me try that again. Let me move up a little bit more. Now I'll move over, and I can get to point B. So it creates sort of this right triangle. You can see there, a little right triangle that's created. And we use the symbol delta. That's what this symbol is right here. It's the Greek symbol delta. That is analogous to the words change in. That means the exact same thing. So delta means change in. So on the graph, I would say that the change in y, or the delta y, is represented here as the height that it takes to get from A to B. And then delta x is the distance that I have to go horizontally to get from A to B. So this is what it looks like geometrically. And geometrically, we sometimes will call this the rise over the run. So this is called the geometric interpretation, or the geometric definition for slope. But algebraically, we would also want to be able to calculate this without necessarily having to have a picture in mind. If I only knew about the points but didn't want to plot them, I could use this formula here to be able to do the calculation for slope. And this is the algebraic representation for slope. That would be y2 minus y1 is equivalent to the delta y, y2 minus y1, and then x2 minus x1 is equivalent to delta x. And so we'll be using this definition in both the geometric and the algebraic interpretation to identify the slope, and ultimately we're going to use this to be able to graph a linear function. And I do have a note here that I want to mention before we end this definition. It says the slope of a vertical line is undefined. Now the reason why that's the case is because if you try to calculate the slope of a vertical line, you're going to end up with a division by 0, which we know is something that we're not supposed to be doing. So that ends up presenting a unique case when we're talking about lines. So the majority of what we're going to be doing in here is non-vertical lines, but since a vertical line is a type of line, it is something that we will address minimally. And the other concern with a vertical line, if I was to draw a vertical line and then try to draw a vertical line for the vertical line test, that vertical line test would fail miserably, and so thus it is not considered a function. So that's another reason why we're going to be treating it as a separate entity and not talking about it with all of the other non-vertical lines.